So I'm told Schwabe had a good joke for the opening of the concurrency session. I don't know who told him the joke at all. But he said, it's unfortunate they asked him to chair that session and another one at the same time. So I have to tell you, we also have a slight problem with the GPU session, which is we've been overbooked. We have too many talks. And so I'm going to have to ask all of the speakers to give their talks simultaneously for us. Okay, I think we're good. We're going to start here with a talk from Guido about Kuiper. So he's going to tell us a bit about how we might do very high assurance GPU programming. Anything else you'd like to say before we start? No?
Nope.
Maybe just go ahead and take it away.
All right, thank you. And you can hear me okay, right? All right, so thank you. Yes, I'm going to tell you about Kuiper. Kuiper is this new language for safe and verified GPU programming that we're building. And this is joined work with a bunch of people, as you can see. And special shout out to Bastian and Jonáš, who are interns with us and helped develop most of this stuff. So since this is the first talk of the GPU session, I thought I'd start with describing the beast we're trying to tame. So what is a GPU? How exactly do they look like? So very briefly, a GPU is a massively parallel accelerator, which you can also call a coprocessor. It's something that is on your machine. It has its own compute, its own memory, but no autonomy. It's the CPU that decides when to run things on the GPU and copies memory back and forth from the GPU memory to normal CPU memory. And GPUs are very important these days because of high compute and LLMs and machine learning and all of this. And it's all about the flops and all about the watts. Like performance is the name of the game. Everyone tries to get the last bit of juice out of these things because they're also very expensive and consume a lot of energy, like Swamy was saying this morning. And so when the CPU schedules something on the GPU, it launches something we call a kernel. And a kernel is something with a lot of structure. It has this execution hierarchy. So whenever a kernel is launched, it consists of something called a grid. And a grid is composed of a set of blocks, and each block is composed of a set of warps, and each warp is composed of a set of threads. And there's possibly millions of these threads, and they're all accessing possibly shared resources, and they're all running maybe simultaneously. And some of these can communicate and synchronize with each other. Some levels can, some levels cannot. So it's really complicated. At the same time, there's a memory hierarchy that sort of mimics the execution hierarchy. There's memories that are close to the threads and close to the blocks. And all of the details are very important when you want to get the final last bit of performance out of these things. So the programmers need fine-grained access to all of this. They need to be painfully aware of the hierarchy, the execution hierarchy, or the memory hierarchy. So great, they sound a bit complicated. So how are they programmed? So you might have heard of a language called CUDA. What is CUDA like? So a bit of a spoiler, it's an extension of C++. But let's study the simplest matrix multiplication kernel that you can write. And matrix multiplication is something that very common to do on a GPU. So the simplest kernel you can write looks something like this. There is a kernel function, and then there's an invocation. And the kernel function up there, we can go through it. The kernel function is going to run, every thread is going to run the kernel function. And this is going to run potentially thousands of millions of times. What this kernel function is doing is, first it's computing its global ID in this whole hierarchy of a grid of blocks and threads. It's getting a unique ID. With that ID, it's computing I and j, which are the rows, the cell of the matrix C, where we're going to compute the product. And then there's just a loop going through the matrices A and B, computing the usual dot product of matrix multiplication, and then writing it out to C at the appropriate position, at row I, column j. And then to launch this kernel, there's this kernel invocation at the last line with the triple angle brackets. And we launch this function with a grid of m times n divided by 1024 blocks, each block having 1024 threads. And these are enough to fill the matrix and compute everything. So already here, there's many implicit assumptions. And this is not so trivial to convince yourself that this works. The first assumption is that A, B, and C all live in GPU memory already. These look like plain pointers, but they are not pointers to the CPU memory. They have to be already in GPU memory. The matrices have to have the proper dimensions. There's no check against that. They have to be stored in row major order, and that's evident from the way we're accessing them, if you just look at the indexing. And also, m times n has to be a multiple of 1024. Otherwise, there are going to be some cells that I'm not computing. Or I would have to round up and then do something on the edge, on the leftovers. So there's already a bit of trickiness in this very, very simple thing. And as you try to get the performance out of this, you need to use more and more complex features, like block shared memory and barriers to synchronize to use it. Vectorized memory accesses. You want to tile your matrices and then access them in strides. You want to access them in different ways. You want to use tensor cores, which are like tiny matrix multiplication units in the GPU. You want to do fusion, like do many things at once instead of going back and forth to memory. And you want to optimize the math. And as you might imagine, this is a bit of a recipe for disasters. So there's memory bugs that can happen very, very easily. There's data races when you're accessing the same data and modifying it. You can mess up the math, and it can be completely incorrect. And you can have undefined behavior if you're not satisfying the preconditions that some of these things have. Like the tensor cores have very precise preconditions. So it's not a great place to be in, especially if you're thinking of applying GPUs to machine learning, which everyone is doing, because you might never realize that you have a mistake. How would you even know? You just get some set of floating points, and maybe your algorithm doesn't work, and you don't know why. Maybe you just made a memory mistake. So naturally, the community, both the PL community and the industry, have been developing GPU languages or ways of making this problem go away. And there's lots and lots of languages. These are just a few, and Saman in the keynote this morning was mentioning many, many more. Some of them are even ML compilers, where you just describe a neural network and you just get the code out. You don't need to do much. But they fall in a classic trade-off between control and safety. And control is like what gives you performance. Control is what allows you to use every last drop of performance of the hardware. So exposing all of that in a safe way is not something that you can usually do. And most of these languages relinquish performance or are unsafe. It's usually that you cannot have both. So the point of this talk is that formal verification will enable safety and performance at once. So we're going to try to have our cake and eat it too. So enter Kuiper. Kuiper is this language for verified GPU programming. It's built on top of F-star and Pulse that you might know. So it has dependent types, a very fancy type system, and separation logic, a very composable way to reason about state. Every program you can write in Kuiper is safe and data race free. It's impossible to make a memory bug. And optionally, you can do full formal verification or full functional verification of the algorithms that you're writing. And it's also highly, highly polymorphic. And that's mainly what I'm going to be focusing on today. But it extracts a simple CUDA. There's no overhead in the code that you're generating. But you can write it at a very high level of abstraction. So in a way, you can also see it as a CUDA verifier, because anything that you can do in CUDA, you could potentially do in Kuiper and verify it and extract it. And this is more about the tool and the practical side. On the theory side, for those who know about separation logic and et cetera, some of the contributions of the paper are a model of heterogeneous CPU, GPU programming and separation logic, including reasoning about where resources live and how they can be accessed. There's a verified account of array views and tensors and layouts and all of the memory operations or memory representations, and some idealized reasoning about floating point that I will mention later today. So if we go back to this kernel, let's try to verify it. This is the kernel function that we just saw. And verifying this in separation logic, this is not too difficult, actually. We just need to figure out what we want to do. So one thing we can do is write it in Pulse. This is what the syntax looks like, and it's very much similar one-to-one translation to what you see there. There's one difference that I'm not computing the global ID. Instead, I'm getting it as an argument, which is a simplification that Kuiper gives you, but it's not essential. So here I'm taking the arrays that are of the proper size. This is statically checked. I'm taking my global ID, which is also a number between 0 and m times n, so I know I'm in scope. And then I do the same thing as I'm doing there. I compute I and j, I do a loop, and I write it out to C. Now, to verify this function, what you have to do is two things. The first one is state precisely what resources we're allowed to access. So the first thing is we state in the precondition of this function that we get read-only access to A and B, and that's what this thing means. And we also get full access, so mutable access, to one cell of the C array, only one cell. And our postcondition here says that, well, the precondition is that that cell pointed to anything, and my postcondition is that it points to the matrix multiplication of A and B in the relevant position. And the other thing I have to do to verify this function is add a loop invariant that explains why this is true. So once we have that, this function is accepted by Pulse and the Kuiper framework, and we can extract it to CUDA and get basically that code you see there, pretty much exactly the same. But what about the kernel call? This we haven't done anything about this thing. So how do we justify kernel calls as separation logic? every thread of the kernel call, the way we're going to model it is that they all run potentially in parallel. Now, this is not exactly true of the hardware, but it's a novel approximation of the behaviors. So if you think of each thread as running, they each have the kernel function kf has a precondition and a postcondition parameterized by their ID. And it goes from pre-0 to post-0 and pre-1 to post-1, and etc. The way we can justify that this kernel invocation as a whole is multiplying the matrices is transform the high-level precondition that we have. We have ownership of all of the matrices, and we can explode them into read-only permission to A and B 1,000,000 times, and then explode the matrix C into pieces, and then give each of these to every kernel function. So there is a stage here that takes the top-level precondition, all of the resources you can access, and slices and dices them into the ones needed by each of the runs of the kernel function. And then the same thing happens in the other way around for the postcondition. Once you have all these separate postconditions of the threads, you can add them all up back into full ownership of the matrix C, and also prove that it is the correct matrix multiplication. These proofs are usually pretty direct. They can get complicated, but for this kernel, they're very easy. For those who know about separation logic and etc., this looks like an iterated star, but it's something slightly different, actually. We came up with a new connective called for all plus, which is similar but nicer to use because it doesn't have any finiteness requirements. So you could ask me about that if you're interested. So once you have this, and I should say, we do this for every level of the hierarchy. So when you take your kernel and you split it into blocks, you do this technique. And then every block does the same thing to split into threads. And then we actually have not modeled warps in this thing at the moment, but it doesn't really matter. We would just add it in the same way. So with this, you get data rate freedom and memory safety because every thread is honest about what they can access, and there's no illicit sharing. So once we have this, what we can do, given that we're in a very highly typed, highly expressively type dependent language, we can take that kernel function that we just had, and we can put it in a record with its pre and post conditions, and we can take this setup and tear down proofs and just package them into the record. And then this record is just, it knows the size of the grid, it knows what function to execute, and it has proof of correctness of why this kernel as a whole is correct. And it just tells me what the pre and post condition are of the full kernel invocation. So I don't have to think about what each thread is doing. So then we can take that old function we had, package it into a record where we choose the pre and post conditions, we prove setup and tear down. And then we just have this package that when C points to something, it will turn it into C pointing to A times V. And then we can just launch it. We can just call it. There's no implicit preconditions anywhere. Everything is all encapsulated. Wow, okay, I'm going really slow. And you can even do this asynchronously. And then you can get exactly the same code we had before. Now, I don't want to do this for every kernel we have to write. You usually have many, many variants of kernels at different types, layouts, etc. So a big point of Kuiper is that kernels can be generalized first by types. You can use type classes to define a single kernel over a family of types. You can use higher order functions if you'd like. In this case, we'll use it to decide how to combine the old value of C with the new one, which is something that's usually done very commonly. So once you have this general version, you can do matmul by just projecting the second component. You can do gem by just saying, I'm going to combine the old and the new value with A and B, alpha and beta. And you can even fuse some function, point-wise function after the gem by just putting it there. And then when you do this with specialization and inlining, you get highly reusable zero-cost abstractions. All of this comes out, and it's just plain CUDA code that without any overhead. The higher order functions obviously do not exist. And this is nice, but we're still working with flat arrays, and we need to do this indexing that gets really tedious. And if you were not in a verified tool, it's a source of bugs. Here, it's just tedious, and it's really awful to use. So the only reason we're doing this indexing is because we're trying to map this two-dimensional object into memory. And you can choose that mapping, and there's the row major mapping. And that's one choice, but there's many more choices. This choice is just saying that the cell ij goes to that position in the array. So to generalize all this, we developed a general theory of arrays that allows you to define these virtual arrays that have any index type, any virtual type, like this matrix up here. That's the way I view the array. And any injection into memory. You get to decide exactly how everything is laid out. You can have holes. You can go backwards. It just has to be an injection. And it's all fully foundational and verified in separation logic. And it allows you to do things like, if you had this other matrix, it happens to be the transpose, If you were to store that matrix in column major format into memory, the memory is exactly the same. So this theory allows you to do view transformations where you just reinterpret one as the other at no cost. This just happens. It's just a proof step, and nothing happens in memory. And this generalizes to tensors of arbitrary rank. You can do tiling. You can take slices of matrices. All of this is supported uniformly. And what's even nicer, it allows you to, use bidimensional accessing on these arrays and just state the layout on the type of the array, and everything is just worked out for you. And then you can change the layout with just a one-line change if you want a separate version. Or even better, you can just make it completely polymorphic on the layout because you're in a very dependently typed language. And this is if you're getting bang conflicts with the layout, you can just switch it with like nothing. And every gem we wrote is layout polymorphic. So yeah, and then you can get the row major version, you can get the column major version, and you can get every combination that you'd like, all for free. You verified it only once. So yeah, I kept saying we're doing verification, functional verification, floating point. So floating point. When we say floating point and functional verification, what does it mean? Is there even a correct result on floating point? Because floating point is very complicated, right? Associativity doesn't hold. If I take x plus y and subtract y, that's not necessarily x. So one way of fixing this is fixing reduction order everywhere. I'm saying the specification could say, I'm adding the matrices elements in this way. But then as soon as you change it, it's a different spec, and there's no reuse. So what we do is we have this abstract notion of approximation that allows you to relate a floating point number to a real, and you can only construct homomorphically by rules such as the one you see there. And it allows you to essentially prove algebraic correctness, completely ignoring numerical error. So we don't prove numerical error at all, not yet at least. But I see this kind of as a feature instead of a limitation, because all of these specs are completely compositional. While if you're doing concrete error bounds, that's a much harder problem that we don't necessarily want to do yet. So the specs look more like this. The result is just a correct approximation of the result. And with the higher order and et cetera, this allows you to do things like, if I want to take the gem from before and numerically stabilize it by using something like k-on summation, which you might know or you might not know, but it's not too relevant, there's just a higher order combinator here that implements k-on compensation for any sum. It just tell me what it needs to add up, and it will just do it for you and compensate it. And then I can take that old kernel I had, change one line, maybe 2 lines, and now I get a k-on compensated version that's much more numerically stable. And the functional proof is unaffected. I don't have to fix anything else. So these are the main features I wanted to tell you about. So what have we done with Kuiper? Let me tell you a bit about evaluation. Yes. About performance. So the first thing, I claim there's no overhead. This is you can look at the performance bar. This is mostly true. We do not find performance difference. We have very performant kernels that we don't yet reach like state-of-the-art, super optimized kublas in some settings. We've done a major many things. Many things are coming: sparsity, attention, LLM pipelines. There's more in the paper. If you're curious, please read it. My main takeaway for you here is safe, verified, high-order performance GPU programming is possible. We don't have to make compromises. This is a full-blown GPU, CPU language. So maybe Lambda is the ultimate GPU language. And consider using it, especially if your agents are doing the coding, which is something we should be scared about. So yeah, thank you, and happy to take any questions.
Thank you. Okay, looks like we got a couple questions here. Manya, if you want to come up and start.
It seems somehow too easy that you just introduced a magic backslash sim or whatever it is in LaTeX operator to capture floating point stuff. What is the semantics of that operator?
Of the approximation relation?
Yeah.
Yeah, so this is a good point. There is none. It's fully abstract and it's not defined. And there's this thing. It cannot be defined. F-star does not expose, or the Kuiper formalization does not expose real bit level details of the floating points. You cannot reason about it. If you could reason about it, I think you could prove this relation to explode it and prove that it's trivial. But since the floating point numbers are also abstract, you cannot, and you can only work with it with these rules. So it's more of a meta argument that this relation is meaningful.
So maybe you could prove some kind of useful soundness property using logical relations or something, treating that as an abstract type.
Maybe.
But it would be very interesting to see what that property actually looks like.
Yep.
Okay,
Yep.
Future work. Thanks.
Thanks.
Okay, 1 second.
Hi. I'm not sure if I have misunderstood, but it looks like you're doing verification.
Can you speak up, sorry?
It looks like you're doing verification at the source level, but the compiler can transform your program in different ways. So is there a compiler that also respects these predicates while transforming your code from source level to the assembly?
So I'm not sure I heard it correctly, but the compiler and NVCC is allowed to transform things, but we're just assuming that NVCC is doing the right thing. If NVCC is introducing a bug, then yeah, that's out of scope. Okay.
Okay. Let me check real quick. I think we're going to stop at 2 questions. Apologies to anyone there. Just make sure we stay on schedule. Let's give Guido another round of applause.
Thank you.